Good morning all. So welcome to the course Analog Circuits. So we'll begin with today the new module. It is a continuation on MOSFET. Okay. So in the previous module we discussed about the BJT and MOSFET, its biasing and small signal operation and models. Okay. So today we'll begin with the module 2. So its first part will discuss about the MOSFET continuation, and second part will discuss about the oscillators, the application of transistors. Okay, so what we cover in this module is there are 5 sections we will cover. So in the first section we will discuss single stage MOS amplifiers. Okay, so MOSFET amplifiers, so that is the application part of the MOSFET. So what are its characteristic parameters? So if an amplifier is there, how we measure its performance? So all these things we will going to see. Okay, so then we'll look at the other aspects, MOSFET internal capacitances and high frequency model. Okay, so we'll be discussing about the model. Okay, so high frequency model. So previously we have seen hybrid 5 model for replacing the, it is an equivalent circuit. Now when we discuss the capacitances effect into the MOSFET, then we come across high frequency model. Okay, and then we see the frequency response of the CS amplifier. Okay, so this you have done in ED lab. Okay, so if any amplifier is there, so you need to have a semi-log graph sheet, and you will be finding out the bandwidth. Okay, lower cutoff frequency, upper cutoff frequency, like that. The MOSFET common source amplifier will find out the frequency response. Okay, so we'll discuss this in the first part of the module 2. Okay, in the second part we'll be discussing the application of transistors, that is oscillators. The 3 oscillators we'll be discussing. One is phase shift oscillator. It is a resistor capacitor combination along with the MOSFET or your BJT. Okay, then we'll discuss the LC oscillators. So that is the combination of inductor and capacitor combination. So they are also called as tuned oscillators. So there are different way or oscillators are there, Hartley, Colpitts and all. So we'll be discussing that. And then we have the crystal oscillators. Okay, so it is a piezoelectric crystal will be used in the feedback. Okay, so all these aspects, what is oscillator, from that beginning we'll discuss this. So that is the second part. Okay, so for today we'll begin with the first section of this module 2, single stage MOS amplifiers. Okay, so it is having 5 different topics. So one by one we will be discussing that in the section single stage MOS amplifiers. Okay, so in this section we consider the various configurations utilized in the design of MOS amplifiers. Okay, so what are the different configurations? Okay, so we can use the MOSFET to utilize as an amplifier. So there are 2 types of MOS amplifiers are there, as I discussed earlier. One is discrete MOS amplifiers, another is integrated circuit MOS amplifiers. Okay, so what are the 2 differences between them? Just quickly we'll revise. The discrete MOS amplifiers are somewhat easier. Okay, so discrete MOS amplifiers are somewhat easier to understand than the integrated circuit MOS amplifiers for 2 reasons. One is the separation between DC and signal quantities. Okay, so DC means biasing, signal means small signal operation, right? So the signal quantity is more obvious. That means we have to go for the separation in this case. Okay, in the discrete circuit case, and the discrete circuit utilize resistors as amplifier loads compared to integrated circuit. So this one, discrete circuit utilize resistor as amplifier loads, like a load resistor RL will be using that. Okay, at the load side. Okay, so that is the discrete circuit case. So in contrast, so in the case of integrated circuit MOS amplifiers, it will employ constant current sources. Okay, so what is constant current sources? So I. Okay, so constant current sources it will use as amplifier loads. Okay, with these being implemented using additional MOSFETs and resulting in more complicated circuits. When it come across IC MOS amplifiers, it is a complex circuit. So it is having a constant current source as amplifier load along with some additional MOSFETs. Okay, so since in discrete circuits, the MOSFET source is usually tied to the substrate. This is regarding the device structures. Very first we told in the MOSFET. So it is having 4 terminals along with the gate, drain and source. There is a body, right? So body is normally tied with the source. That's what this point is telling. the MOSFET source is usually tied to the substrate. That's why the body effect will be absent. Okay, so that is the assumption. Therefore, in this section, we will not take the effect of body effect into account. Okay, so body effect is nil. So just one point we are discussing, and also in some circuits we will neglect R0. So in the hybrid 5 model of the MOSFET in the previous section we have taken, right? VGS is there, then a current source is there, GM VGS. Along with that, a parallel R0 is there. Okay, so that R0 sometimes for simplicity purpose we will not consider. Okay, so it is there, but simplicity purpose it is not used. Okay, so keep the analysis simple and focus our attention at this early stage on the salient features of the amplifier configuration. So here our main focus is on amplifier configurations. Okay, so that's why. So these are some of the points to remember before we proceed to the MOS amplifiers. Okay, so now there are different types of MOS amplifiers are there. The various configuration as you had in BJT, common base, common collector, common common base, common emitter. Same way in MOSFET amplifiers, you have the three terminals, gate, drain, and source. Accordingly, you have common source, common drain, common gate amplifiers also you can configure. Okay, but the most favorite is common source amplifier. So that's why all your circuits will be based on common source only. Only particular we will be considering common gate and all there in the book, but in your syllabus it is not there. Okay. So this is the basic structure we will be following for all the coming MOS amplifiers. Okay. So next coming MOS amplifiers will be this is the base. Okay. This circuit only will little bit modify and will bring out new amplifier configurations. Okay. So figure shows the basic structure of the circuit used to realize various configurations of discrete circuit MOS amplifiers. Okay. So this is just an reference circuit for us. Okay. This figure also indicates that the DC current and the DC voltages resulting at various nodes, that also indicated here. Okay, so this is the MOSFET. So normally MOSFET VG value is here is 0 volt, and this is the RG connected to the gate terminal. So this is the gate to source voltage, and then drain resistance. Okay, drain side it is connected. Then this is the VDD supply. Okay, so then ID is equal to I we have taken. Okay, so ID is nothing but drain current. So instead of writing ID every time, so just I is substituted here. The same ID will flow in this source terminal also. That's why it is shown as a constant current source. Okay, that's what we told amplifier loads, right? And there is a supply VSS also. This is a DC supply. So then you know some of the equations, right, from previous discussion. So VD is given as VDD minus IDRD. Okay, so this VD, the drain voltage here is nothing but the VDD supply voltage minus the drop across the resistance, that is ID into RD. Then VGS you know already. So VGS minus VT is equal to V overdrive voltage. So it can be written as VGS equal to VT plus V overdrive voltage. Anyhow, you can write that. So this is second equation to remember. Then what is V overdrive voltage? This is written from the ID equation. Okay. So last time when we are discussing the GM, that is the transconductance, we told you there are different ways we can write it, right? So very first equation, basic equation of the MOSFET, what is that? ID is equal to 1 by 2. So recall that. Okay, Kn dash W by L. Writing it will take time. Okay, but still I will write. So Kn dash W by L. No need of bracket. I took that. And then what you have, VGS minus VT square, or you can write it as VGS minus VT is equal to V overdrive voltage. So I will substitute as V overdrive voltage square. So this is your basic equation. So now what I have done here in this diagram is ID I have substituted as I. Okay, so ID I have substituted as the I have taken. So from this equation now, so if you rearrange the equation, if you write for V overdrive voltage, so what is the equation you are getting? This one. Okay, so what is that? So if you just write for V overdrive square, so this 2 will come over here. That becomes 2 into I divided by Kn dash W by L will come. Okay, so that is for V overdrive voltage square. Now if you write for V overdrive, then it will come square root of, okay, square root of 2 into I by Kn dash W by L. So this is the equation. Okay, so I told you the same equation can be modified in different manner. So that's why be cautious. Okay, so all things you have studied, no need to worry. Okay, so this is the basic circuit. On that we'll be going through different amplifiers. So now before we start off with the MOSFET amplifiers, we need to know the characteristic parameters. That means, so when you have taken a mobile phone, or if you want to purchase a new mobile phone now, so what you are looking in, okay, if you are going for Amazon, Flipkart, what parameters you look for. Okay, so now present end is 6 GB RAM, 8 GB RAM is going on, right? 256 GB hard disk, okay, 128 minimum, right? So will you go for the lowest one like 64 GB, 32 GB and all? Okay, so it is you will not go for, right? So you have to see some set of parameters. Even the body of the mobile you will see slim, okay, lightweight, okay, and then you will see the screen size 6.457, like that you will be looking at, right? So that also you look at. Then camera resolution, then quad camera is coming now, right? So triple camera is also gone now, dual camera also now gone. So 4 camera, you have density and focus, everything is there, and better selfie. Okay, so all these features you will be looking at, along with the operating system Android 11 is there. Okay, so this is something you will look for, right? And if you go for that, if you say resolution, okay, so it is also defined way somewhere way. When we say RAM, it is defined. When we say hard disk, it is defined. When we say screen size, it is defined. When we say touch screen, LCD or OMLED, something it is coming, right? So it is defined, that parameters are defined. Same way in the MOSFET amplifiers, whatever parameters. So we have to measure the performance, right? Because MOSFET amplifiers are utilized in the everywhere for amplification purpose. Okay, it may be in communication circuits, or it may be anything, anywhere. Okay, so you need to measure the performance. So this MOS amplifiers which I have configured, how much it is going to give the result, right? So even the industry people for mobile, they will do like that research. No, if I do this combination, how much pixel I am able to support for this processor, right? And battery size also you have to look at, right? The same way, this we have to keep into mind, and we have to define the parameters. So that's what I am doing now. The next topic, characterizing the amplifiers. Okay, so characterizing amplifiers, we learn about the different performance parameters of the amplifiers. Okay, and again there are two types of amplifiers will be discussed: unilateral and non-unilateral amplifiers. Unilateral amplifiers means it is pertaining to some certain block only. Okay, so normally when we say amplifiers, it is not using only single MOSFET. It will be using a hundreds of MOSFETs or thousands of MOSFETs to do the amplification, or to make a integrated circuit. We told, right, integrated circuit uses millions of transistor or millions of MOSFET in general, right? So when we are using that, it will be using in some combinations, right? It may be cascade, it may be cascode, it can be Darlington configuration. So like that, different configuration, it will be connected one to one. Okay, so the output of the uh, first amplifier will be connected to the input of the second amplifier. Like that, it will be having some configuration. So when we are particularly discussing one particular section, okay, so when we are saying our whole college now, so it will be having some 50 plus rooms, okay, including the labs and all. But when I'm considering only about some particular room, okay, and I am telling the cleanliness of that room, then it is called as unilateral. Okay, and when I take whole into picture, then it is called as non-unilateral. It may be more than one room. Okay, the same way for the amplifier case here. So unilateral and non-unilateral. Whatever we are discussing in MOSFET amplifier, it is non-unilateral, but still I have taken unilateral because just to understand some parameters points. Okay, so just 4 types of amplifiers you have in unilateral, and this is general types of the amplifier. Okay, so first amplifier is the voltage amplifier. So this we have discussed already in the 2-port networks in network theory. Okay, so where we have discussed the 4 different parameters. So in the case of Z parameters and Y parameters, we have discussed this. So when we take the ratio, both voltage comes means voltage gain. When we take on both current means current gain. When there is a ratio comes from voltage to current, it is a trans resistance. When there is a ratio comes from current to voltage, then it is called as trans conductance. The same way these amplifiers are named over here. Okay. So voltage amplifier is the first type of unilateral amplifier. So its circuit model looks like this. So it is having an input Vi and an input resistance Ri. Then it is having a voltage, so dependent voltage source which depends on the voltage. So it is called as a voltage controlled voltage source. So AV into VI, its value. Okay, AV is the voltage gain, VI is the input voltage, and R0 is the output resistance. And this configuration, or it is a Thevenin's equivalent circuit. When you have a voltage source, there is a series resistance will be there. The same thing can be converted into a current source in parallel with resistor. That is Norton's equivalent circuit. Okay, so you know these models and all, how we written in H parameters, Z parameters. Okay, the same thing I am discussing here. So in the case of voltage amplifier, the gain parameter here is the open circuit voltage gain. So open circuit voltage gain, how we define? It is denoted as AV0. Okay, AVO. Okay, so don't. It is a AVO. Later we will discuss AV also. That is voltage gain. Just we call voltage gain. That is AV. This AVO meaning VO by VI when I0 is equal to 0. Output current is equal to 0 means what? Output is a open circuit, right? I current is 0 means open circuit. That's why it is called as open circuit voltage gain. Okay, so this is the definition of the voltage amplifier. Okay, the ideal characteristics of voltage amplifier is its input resistance is very high and output resistance is very small. Okay, so input resistance is very high, it is indicated by ideal case infinity, and R0 is 0. This is the ideal case we are telling. Okay, so this is about the voltage amplifier, and this is the parameter here, open circuit voltage gain. So next type of amplifier in this unilateral is the current amplifier. Okay, so the name itself says, so it is a having a current gain. But how we tell that? So this is the model, same way. So input current II, then input resistance Ri. So then you have the current source here. In the case of current amplifier, you will have a current controlled current source. Okay, so this is the gain. Okay, it is called as short circuit current gain, AIS, denoted as AIS into II. So it depends on the input current. So this is a Norton's representation now. So since current source is there, so resistance came in parallel with that. Okay, so R0 is the output resistance. Okay, so how you define its gain parameter? It is called as short circuit current gain because it is denoted as AIS. AI means just current gain, AIS means short circuit current gain. Okay, so that O means open circuit voltage gain, S means short circuit current gain. Okay, so don't confuse this. These are number of parameters we are going to define now in the non-unilateral case also. Okay, so it is defined as output current by input current when the output voltage is 0. Meaning what? Output is short circuited. So voltage is 0 means what? Short circuit. Current is 0 means what? Open circuit. This you know in network theory. Okay, so this is about the short circuit current gain. The ideal characteristics of the current amplifier is it's just converse of the voltage amplifier. So input resistance is 0 or nil or very small value, and output resistance is very high. Okay, in ideal case we say infinity. Okay, so this is about the current amplifier. So now other two amplifiers are nothing but either it will be having output voltage by input current or output current by input voltage. Okay, so that we call it as trans resistance and trans conductance. Okay, so the third type is trans conductance amplifier. So its model is a combination of the previous two. Okay, so this one is the voltage amplifier input side. Okay, so you had Ri and input is Vi, and this is the combination of the current amplifier where you had the current source and the resistor in parallel. But the parameters will change here because it depends on now voltage. It is called as voltage controlled current source. That is the change. So we learned four different types of current sources, right? So dependent sources, in that it will come as now voltage because it depends on input voltage Vi now. Okay, so voltage controlled current source, and its ratio will be normally the I0 by Vi. Okay, so that's why it is trans conductance denoted as GM. Okay, so that is the short circuit trans conductance. Why it is called short circuit? Because this we have copied from the current amplifier. Current amplifier case I0 is equal to 0, right? Sorry, V0 is equal to 0. So its ratio is I0 by Vi. Output current by input voltage when output is voltage is 0, meaning output is short circuited. So it is amps per volt. Okay, trans conductance, or it is Siemens also we say. Okay, so this is about the third type of unilateral amplifier, trans conductance. So its ideal characteristics is So it is using, I told you, combination of this one, right? Voltage amplifier and current amplifier. So input side it is voltage amplifier. Voltage amplifier case input resistance is very high. That's why infinity. Second part it is using from the current amplifier. Current amplifier case output resistance is very high. That's why you got R not equal to infinity. So now you can tell the last one. So its input side will be of current amplifier type and output side will be of type voltage amplifier. Okay, so accordingly all equations will change now. So we call that type of amplifier as trans resistance amplifier. Okay, so the fourth one is trans resistance. Circuit model, so it looks like C here. So current amplifier side, current input II is there, RI is there, and this is equivalent to the voltage amplifier output side. So where you had the voltage dependent voltage source here, and there is a resistance in series with it, Thevenin's equivalent circuit. But here, so its ratio is now output voltage by input current. So V by I, that's why it is R. For representing trans resistance, RM is written. Okay, so RM into II. So this is called as current controlled voltage source. Okay, so it is a current control because input current is controlling this voltage source. Okay, so that is the difference. Similarly, we write the gain parameter as open circuit trans resistance. Open circuit trans resistance RM, denote it as RM, and given as V naught by II when output current is equal to 0, means what? Open circuit. When current is 0, open circuit. So it's given as voltage per amp or it is given as ohm. Okay, so ideal characteristics is, so in the case of current amplifier you had input resistance is 0, that same thing will come, and the output side you have voltage amplifier case R naught is 0, so the same thing it will come over here. So that's why in the case of trans resistance you have both resistance is 0 or it is very small. So this is about the summary of 4 types of unilateral amplifiers. Okay, so these are defined because based on this only we will continue the discussion. In non-unilateral, so you'll be having many blocks, so that's why the parameter set also will increase. Okay, so that we look at now the non-unilateral amplifiers. Characteristic parameters of non-unilateral amplifiers. So we'll be discussing this in detail. So how much time is there? That much I will discuss, and remaining I will continue tomorrow. Okay. So this is the basic circuit I will consider here. Amplifier is shown as a block here. So this is the amplifier block. I didn't show here it is a MOSFET or anything. In general, I am discussing. Okay. Because later I am discussing op-amp also, maybe BJT also it will apply. MOSFET also it will apply. Okay. So input current we have shown II. The output current we have shown I naught. And the input voltage we have seen VI. And the output voltage is taken across the load resistance RL. So here 2 different cases will come in non-unilateral amplifier. So either load resistance is connected or not connected. Based on that, you have 2 different values of V0 you can measure. Okay. Similarly here, this V signal and R signal. So these are the signal components. So this is going to be amplitude, right? This signal only we have to amplify through the amplifier, right? And that will be collected across the load resistor. So in the auditorium, if speaker is speaking, so his input is given to a mic, right? That is nothing but your V signal. And there is a resistance. So it is a common component along with that, right? And it will be passed to an amplifier. So you have seen that it is connected to a wire or a wireless, right? So you have seen the mic and it is connected to some box, the nearby black box, and they will tune that, right? So that is your amplifier. There you have the amplifier box. And from there, that amplifier box output port, it is connected to the speakers. You have seen anywhere you go to function, there are black color big speakers will be there, right? So they are connected. So that is again connected. So they are nothing but this load. Okay. And across that you are getting the output, magnified output. Okay. The same circuit, it is represented like this, a general circuit for amplifier. So now we'll define number of parameters here. Okay. So if the this is signal, R signal or V signal is connected or not, or RL is connected or not, in that case, how we define the same parameters, 4 different parameters we have defined. Now that only will do it in 2 different sets. Okay. So first one, input resistance with no load, meaning what? The RI, the input resistance with no load, we call it as RI now. Okay. So we denote it as RI. So which is given as VI by II when RL is equal to infinity. RL is equal to infinity means what? no load. Load is not connected. Okay. So load is not there. It is not, path is not there means it is infinity. Okay. Then second set, input resistance will define. So this is if they just say input resistance, meaning it is connected to a load. Okay, load is connected, then we just change the denotation here. So here it is just Ri, here it is Rin. Okay, and it is just given as Vi by Ii. There is no condition here. Okay, here it is condition is there. What is that condition? No load is connected. Here load is connected. Okay, so see this difference. So this notation is very important. Okay, so to understand, so you write down that. I'll give you the notes so that you can clearly understand that. Okay, simple it is. Only thing is clearly how to differentiate the notation. Next set of parameters, open circuit voltage gain. Previously I defined in the unilateral amplifiers, right? Open circuit voltage gain is denoted as AV0, right? AVO, sorry. AVO, it is given as V0 by Vi when RL is equal to infinity. Means what? There is no load connected. RL equal to infinity means no load connected. If load is connected, then we call that as just voltage gain. Then we call that as just voltage gain, and notation also just AV. Okay, here AVO. AVO means you understand it is load is not connected. Here load is connected. Here it is given as just V0 by Vi. Okay, so the both different cases. Similarly, current gain also, short circuit current gain denoted as AIS. It is I0 by II when RL equal to 0. RL equal to 0 means what? In the case of current gain, we call that as RL is 0. Okay, in the case of voltage gain, we call RL equal to infinity, meaning again RL is not connected. Okay, so when RL is connected, we call that as just current gain denoted as AI I0 by II. There is no condition to define that. Okay, so hope you understood input resistance, Ri, Rin, AVO, AV, AIS, AI. Now similarly we'll continue short circuit transconductance. In the case of transconductance amplifier, we have seen this, right? Gm equal to V I0 by Vi when RL is equal to 0. So in the case of unilateral amplifier, nowhere I have considered load, right? It is a just ideal amplifier. That's why the same thing it will holds good here for no load case. Okay, so RL is 0, so that's why I0 by Vi. So it's now load connected part we define as, so later I will take that, maybe next it is there. Okay, so overall voltage gain in that case we have. Okay, so next till here we have discussed. Then output resistance of amplifier proper. Amplifier proper meaning here it is not connected with any RL or V signal. So just a amplifier. So your mic is also not connected now. Your speaker is also not connected. Just your amplifier set we are going to measure. Is it the amplifier set is working properly or not? Okay. When we check its input and output, just we give some testing method will be there. Just Vi something will apply. There is no see here. Diagram is shown here for your reference. Okay. So V signal is not there. R signal is not there. And there is no load resistor also not there. Okay. So we have shown like this Vi and there is a new set of voltage I have shown Vx and Ix just to define that ratio. Okay, so just we are giving some current to that amplifier and we are measuring the voltage. Okay, so in the case of Thevenin's equivalent circuit we have done that, right? If there is no DC voltage source is there, then what we have done, 1 amp current source is applied and we have measured the voltage, right? So then voltage by 1 amp is nothing but your resistance. The same way we are going to measure the here output resistance when Vi is equal to 0. That we call as output resistance of amplifier proper. Similarly, when the V signal is 0, so V signal is not there, whereas RL is there. So then we call that as output resistance R out. Okay, so that is about Vx by Ix. So I will be telling number of remarks about that. Okay, so then you will be clearly understanding what is this points about. Okay, so this is the case of output resistance where V signal is 0. Okay, R signal is there and this one. Okay, so Vx Ix same way. So now we call that difference as R out. This RO is R out. Same way Ri and R in we called, no. So R in we have defined with respect to load. Okay, and output resistance we define with respect to input voltage. There are two sets of input voltage. One is Vi, another is V signal. So in this case it is Vi is 0. In this case Vi is there, V signal is not there. Okay, V signal is 0. Like that, we will define the output resistance, converse. So next two sets are that is open circuit overall voltage gain. Okay, open circuit overall voltage gain, it is given as GVO. Okay, so it is given as V0 by V signal. So what is the difference here? AVO is open circuit voltage gain. AVO is nothing but V0 by Vi. But now we have taken Vi previous signal, that is V signal we have applied. No, that ratio we have taken V0 by V signal when RL is not connected. Similarly, if we call that overall voltage gain GV, it is just V0 by V signal. Okay, so these are number of parameters with respect to single stage MOS amplifiers. Okay, or characteristic parameters of the amplifiers. So you should know the knowledge of these things. Okay, and also the relationship between one to one. And then later we will take one problem to understand this. Okay, how we solve the amplifiers problem. Okay, now number of equivalent circuits are there. Okay, so first equivalent circuit we have V signal and R signal. Along this is, you know, MOSFET. There are different types of MOSFETs we have seen, amplifiers. Okay, current amplifier, voltage amplifier, trans resistance, trans conductance. By looking into this dotted line, you have to identify which equivalent circuit is this. Okay, so I will not explain that much. So remaining additional part I have added here. Okay, so this is MOSFET equivalent circuit. So this is a voltage controlled voltage source. Maybe it is a voltage amplifier. V signal, R signal connected, and here RL is connected. Okay, so this is a equivalent circuit. Similarly, B equivalent circuit. I will be referring this in the remarks later. That's why I have named it. Okay, BC. Okay, equivalent circuit ABC, like that. So you have to note down this. Okay, so before tomorrow's class, everything should be copied in your notes so that when I am discussing tomorrow, this will be easy for you to understand. Okay, next we have another thing. Okay, so it is the GMVI R0. So it is nothing but the transconductance amplifier because of this GM, right? So it is a transconductance amplifier. So V signal, R signal, and RL are connected. Okay, so then the same thing is converted into a Thevenin's equivalent trans conductance only. So V signal, R signal, Rin is there. So this is just changed to V signal. Depending on V signal we have made. Okay, so and R out. So this is little bit modification to same B circuit, it is made C. So these are three different equivalent circuit we have referring when we discuss about that. Okay, and then these are the relationships. Whatever I have taken parameter, no, these are the relationships we will use it when we solve the problems. You need to remember this. So Vi by V signal, where we use Vi at the input side of the amplifiers. So Vi will come near to the amplifier set, and V signal you are applying right from the mic and all. Okay, so that ratio is given as R in divided by R in plus R signal. What is R in? It is the input resistance with no load. Okay, when you take input resistance with load, R in. Ri means input resistance without load. Okay, so it is with load. So R in by R in plus R signal. Then AV, voltage gain, is nothing but open circuit voltage gain into RL by RL plus R0, output resistance. Then AV naught is equal to GM into R0. So this is the relation. So no derivations are there. So just you need to know. Okay, so number of. Then GV. Okay, so it is overall voltage gain is given as Rin by Rin plus R signal into open circuit voltage gain into RL by RL plus R0, which is nothing but the same thing. Okay, so Rin by Rin plus R signal into AV. So AV only I have substituted here. Okay, so this AV is nothing but AV naught RL plus R0. The same thing it is substituted here. Okay, so GV is nothing but AV into Rin by Rin plus R signal. Okay, so like that also you can remember. Then GV naught is equal to Ri by Ri plus R signal AV naught. There is a clear difference between in and I, right? That's how it is. So this is a with load. This is no load. That's why here no load Ri has come. Here with load RINS has come. Okay, that is the difference. Then GV equal to GV naught RL by RL plus R. So these are number of relationships we have. So using this, we will be doing the characterization of the amplifiers. Okay, so you should be thorough with this. All these relations you have to go through. You have to write and practice this like trigonometric relations. Okay, fine. So there are a number of remarks are there regarding this, so it will not complete today since 2 minutes time is there. So I will take this continue this in tomorrow's session. Okay, and one problem is there, that also I will discuss based on that. So I will send you this notes, so you write down that and study once before joining tomorrow's class. Okay,